Perfect, perfect. Then it works at least. And I would say if it's not working, yeah. Yes, the normal one. Not the viewer. The viewer doesn't need any license. It's only for analyzing simulations. You need the normal one. Viewer is only like Adobe Reader. You can't edit something, you can open it, read it, but you can't do. No, not to Treasury. Please send the error code not to Treasury or to where you got the mail from, but to, I think it's a.becker or office at becker3d.com. See? See, I think it's also here on the website.
Oh, no arreglan los problemas técnicos en tu casa. María, como te extraño.
It should be anything at becker3d.com.
Capaz isso te.
Please send it to that mail address, not to Treasury, because Treasury is only the download file. But you already got the Excel, right? You got the Excel file, so the executable, the installer. Everyone got that, right? Okay, you got that, installed it, and after that you still got some errors left. In the end, it should look something like that, most likely with a dark background, but you can change that very here. You can change that. Background or foreground, you change that to colors, you can change that too, okay? If you want. Yep. Super. Okay, perfect. Now we got the, yeah, super, thanks. This should work a little more stable. Good. Yeah. Okay, who has this screen open now? You as well? Oh? Not working on, okay, you do have both Macs. And it won't work with a virtual machine, I guess, because it needs an Intel or an AMD CPU, most likely. Yeah, it looks something like
this is starter screen. What should we put in here?
Perfect. Yeah, there's okay.
Or we just
typically on the first start there is something like a welcome screen because it's your first time opening and stuff like that. You can do some. You can see here a belt conveyor, a rotating stack mill, and a V blender. We will do one of those now in the following. You can do that to get started, but you can skip that. You can even click on the bottom left. There is don't show again. If you don't want it, it's a welcome screen, right? On the top you see quick start user guide. We will explain that now, okay? So we will do that step by step. Take a little look where the documents are. So I would really recommend you two especially because it's two have Macs. Please join some colleagues over here with I don't know, HP or Lenovo, so you can look over their shoulders a little bit, getting familiar. And also you should form some groups in the end. So probably some volunteers, get your colleagues into your group, work on a project, find something. And I also wanted to encourage you today on your own examples. Some of you already sent me some ideas. Screen here, most likely a mixer there. Someone already sent a screw feeder, also a good idea. So anything that's involving parts that are moving and particles on the other. But today we will look at the graphic user interface. No scripting, no program. We just getting to know the user. Get them out here. Okay. Please, if it's not working now, send your mails in the meantime and look at your colleagues' computer so that you see the screen that we have also here. As said, I changed my background color to white. It's a little better. But it's also okay. If you have the webcam, okay. Who is not this screen now? Anywhere near favorite filter on your own computer. So, you don't have it?
Cambiare
This send a mail, right? So to info factor.
option.
Yeah.
Modo.
Yeah.
Devi ponerle un
You
basic.
send it from your mail address.
¿Porca? Ponle un mono. Acá está decirte.
So, just the sheet in. There we go. Send it to Alex. He knows there
Ahí está.
and we can do on it. And I would say, please change your seat probably. Maybe probably look.
Cambiaste
No,
el
damn. But you send the mail, right? Okay, great.
Clear.
In the meantime, we will do one example, another example, check again, and it's
Background.
there are some lessons activated.
Ese está blanco.
On April today, most of you should running that yes, sorry for that. And join some group. So the other guys don't need to be too no worries, okay? So let's start. You say you can see that here. Here is the 3D screen. You click the normal mouse button and you can like CAD. Change anything, select anything here. Just view it. Viewing pan. So what you do on the left side has an effect on this 3D view. So here you can see your object in 3D. It's not say, yeah, fantastic. By now it's the rectangle. Any idea what the
The volume where.
yeah,
No.
close it up. No,
It's
it's
the-
the computational domain. So everything in this domain is working. Outside that domain,
In option.
inside that domain, it needs to be inside the computational domain. Remember that we talked about the grid and subsailing and contact partners, right? You can see that here. On the set, and this is the setting that find neighboring partners in those sets. Remember that? Something, right? So this is the this is the most important. You can enter stuff and it appears on the right side. So if we go here, some of the stuff we don't need. Those materials, that sounds interesting. Interactions sounds interesting as well. Particles, most likely we can define some shapes of particles here. So this is the stuff where we set up the things that you can see later on the right side. On top, just a short thing, it's similar like in every other program. You have some ribbon bars, you can change view, toggle on, off, visibility. You learn that, right? So let's start with something very simple. We want to, let's say, we want to have a very, I think we will start just with an example so you can learn what it is. We want to make a surface, just a floor or a plate or anything, a ground, where we want to pour particles on it, right? Forming a heap, like we have plate in mid-space, and then a source where particles are flowing onto here, forming a heap. That's our goal. Very simple, like a, let's say, a cone of particles. That's our ultimate goal. So what do we need?
Particles.
Yes, we need particles. Let's start with that. We let particles here. Here, it's okay for now. We call that particle. And, oh, there is no material defined yet. Let's say, yes, because we want to have a material defined, that is our particle material. Okay, now we have a particle. If you want, you can double click that. Or you can also switch in these inside ribbon bars to change some stuff. So we don't have defined the size of the particle yet. We haven't defined what it is made of. We have to define some details in its shape. But we said it was a sphere, so most likely if I double click it, it jumps to sphere. So you have that particle, define that name is particle, probably I rename it because I want to name particle underline 1. So it's easier that it is my first particle shape that I create. Particle 1. And if I double click it or go to sphere, I can select a particle with the name particle 1. And it is made of solid default material. That material was just added when I clicked yes. Remember that? There was this pop-up. There is no material. So should I create one for you? Yes, please. So I have a solid default material. Just leave the collision offset on it. But interesting, there can be set a radius. And if I change that, I already see something. Oh, cool. So I see our particle with 0.1 meter radius. It's quite big. Let's say we have a particle with 2 centimeters radius, diameter instead of it. Because let's start with bigger particles. The smaller they are, you remember, time step increases. Small particles, small time step takes forever to compute something. The bigger the particle, the better. Let's start with a 2 or 5 or 8 or 10 centimeter particle. Let's say 1 centimeter radius, 2 centimeter diameter. You can see that here. Zoom in. If you double click your middle, 1 minute. If you click double on your middle mouse, so on your mouse wheel, it makes a zoom fit. It's the same as somewhere up here should also be the zoom fit. I guess that one. Yeah, zoom fit. Because if you are anywhere like that, you can just click zoom fit and it jumps to it. Yes. I think it's moving too fast. Okay. I will repeat it anyway, right? We will add a second particle. This is our first one. We will add a second one as well. We make a mixture of 2. Wow. Everyone following so far? We have not done a lot. We have just defined the particle in its shape, not more. We have said sphere. Cool. So we have a size. Particle has a name. Cool. Some information down here. No mass. Why is that? We have a volume but no mass.
We can define the material. We haven't defined the material yet.
Yes, material is missing. Absolutely right. So probably let's switch to a different entry here. Material. Oh, what can we see here? Solid default. Sounds familiar? Yes, it is the material the particle is made of. So let's probably change the name, okay? Change it by clicking on rename here, or you can also, like, I think you can also, like, small, like here, rename, and we call that stone material or whatever. Simply call it. This is the material. The other material. Plane.
Here when you select the type, it says solid fluids and fluid-solid interaction.
Yes, you're looking into some stuff you're not supposed to look into. Yes, okay. No, the software can do a lot more. You can do SPH simulations. We outlined that a little. We're working with particles, with solid particles and nothing more. You can also do, you remember, slushy material, damp brakes, something like that. Probably a hockey puck falling into water, oil simulation, gearbox simulations, multi-body dynamics. That's beyond that what we do. For now, solid.
Yeah. But in bulk, we only solids, not fluid-solid interaction.
You can do that. You can play around as much as you want. There are some examples also. I would say for now, okay? This example now.
Okay.
We try to set a solid, rigid plane that stays there, no interactions, no movement at all. Plane, pouring particles of 2 sizes on the plane. Starting with one, then with the other, and then probably a mixture. Very simple, step by step. Getting there. We can also do some water stuff. We can do extensive contact models, but start with the dry, solid part on a dry, solid ground. Okay. Everyone so far with the particle material creation? So we created a particle here. After all, I would suggest you to start, if you start ever again, if you want to write that probably down a short, let's say, handbook or red line to follow in your modeling. Start actually with the materials that you probably want to have in your system. So let's say we have a rock for our bulk material, or name that bulk, or name it limestone, whatever. It's the material for your rocks, for your particles. Add another one, solid, with the name, for example, steel or floor or wood. So something that is not your part. Let's call that steel, because we want to make our floor out of steel or a liners out of steel. A belt made out of rubber, for example. So define the materials that you have first. So you have two materials, and then go on with the next step. So start with the actual materials definition. First thing. Okay, now we have at least two materials. Yeah, most likely we need two, in most cases. Again, if you double click it, you can change some details on that. Now we have set a name, but not yet a density or anything more. Those three are not optional. Those three need to be set. Density, let's say our rock should have 2,500 kilograms per cubic meter. It's the solid density of our sphere. Remember, our solid density probably is not the same as the real physical one, because we have a sphere and not a real rock structure. Probably we need to fine-tune that, but let's keep with that. Let's start with a good value in the range of a real material, right?
Yeah.
This is not that far away. Probably a bit more, probably a bit less. Okay, like concrete or whatever you want to. You can also say rice. You can also say apples. So it's the material your sphere is made. Good. Shear modulus, oh, and now again we're back to, you remember last time, we talked about shear moduli, like gigapascal or megapascal, what is it? And we said, setting the shear modulus as low as possible would increase our computational speed. In reality, we have gigapascal. In our system, I would really recommend you, and you can also write that down, density you can choose a real one. Shear modulus, please stick in the range between 10 to 100, probably 150, not in the real physical one, because I had colleagues putting there, I don't know, something like that. Much too much, your computation will crash and it takes too long. Start with, I don't know, 20. Please don't go below 10 or 5, that's the lower limit, because it's very complicated. Remember last time I painted a sphere penetrating the surface. And it is okay, so it finds a stable state with a small penetration in the surface. And the richer, so the higher this value is, the less overlap is allowed to the manual equilibrium. So if you have a very low shear modulus, about 2 or something, the sphere is sinking in the surface. So there is a vertical overlap, and at some point, it's too much. Okay, it's a little bit, let's say, overcompensated. So probably stick with 20, 50, 100, let alone the level of the difference. In the end, the difference is that you can iterate a little faster with slight offset in the accuracy. Slight, which is not really relevant in our case, right? Because, come on, we already said our sphere represents a stone. So probably shear modular adaptation is not the first thing. So stick with 20. And the last thing, yeah, Poisson ratio, you know that, about 0.2, 0.3, just send it as it. This is a good thing to start. Probably a screenshot of that will help. So this is a good start value. And also, you can save that. You can also open it again, go through the details. There are lots of examples on there. I will show you again. But please, let's start with very simple example. Good thing, there was a hot word, save. You know that symbol, right?
Mm-hmm.
Or Control S for Control Save. Let's click that, and it opens some folder. Probably a most default folder, whatever. And I say I want to save that on E simulation. No need to worry about that, except one thing, especially for the German guys. Anyone with an umlaut in his name or a sharpest S. Please be aware. Yeah, be aware. And you know, I think it's not the first time for you, right? Any symbol that is okay for a website or email address is okay. So no sharpest S, no umlaut, no diameter symbol, nothing like that. Simple uppercase, lowercase number, space. That's okay. That works. But yeah, and I had some problems last year. Lots of and finding out that this is the problem. So, simulation. We see that it's a so folder, and we call that just for me to over 0. I like the underline. And save. So you now have saved this simulation setup that you So it's 2025. I have the 01 test simulation TPCAE, so pre-particle CIE file. And a folder that the system automatically should be empty more or less. Yeah, not data. This is the structure that is set in the factory. So far, take the simulation file, make the particle and the material. Yeah. Anyone some trouble so far? I still did my program full. It goes. So just reopen it. If it crashes, if something happens, probably there are some issues here and there. Just reopen the system. I already crashed it all the time. In my case, I enter something, a zero division something. But just reopen it and you can again open, select, save. Maybe one thing also, if you remember, when I said we simulate something, we simulate time steps. So we simulate time step, time step, time step, and then we save the time step, time step, time step, time step. We save it again. So we probably save our simulation every second, okay? But between 0 and 1, 1 and 2, 2 and 3 seconds, there are time steps that we compute. So we compute, save. Compute, save. So in the end, we can play a more or less video between those saved time steps. So this data must be stored somewhere. And this data is the working place. So, or the working folder. And this can also be changed here, working directory on file, working directory, where your actual simulation files should be stored. And this can be changed because they can be wide used. To show you how this looks like, just an example. Let's open my doc Russia, but from SPM, that one is nicer. So this is, for me, a common workplace. So I have a working directory where I have several simulation files, all TPCAE, ZCAE. These are not really big. 2 kilobytes, okay? Not that big. Actual simulation file, anywhere here, 250 megabytes. So there's lots of information in those files. So if this is not much. This is just 0.008 seconds of simulation. There's 2.9 gigabytes of storage. So this is quite intensive in terms of data storage. So you need to set your working directory more or less with enough space, I would say. In your case, not that much, not 500 gigabytes, but a few gigabytes still should work. Yeah.
Yeah, I save it, and it tells me that it's saved successfully.
Yeah.
But in the folder that I select,
No.
now because before it doesn't appear anything.
Okay, TPDM is the actual first time step. I will come to that.
Okay.
So please also maybe set your gap. So set the same solid 25 as before. So just simulation and working directly the same should work again. And this should be recognized by the system. So if you restart, the working directory should stay the same. And otherwise, there's you anyway. There is no. So we have something set up, saves the file, and if I close the program, or sorry, I'll close the view. So if I now select that file and create and And just a short recommendation, kind of say as Control S. So we have still particle. If we click on particle, we can see it is made of the system recognizes that we renamed the mirror. So we have 2 centimeters diameter, 1 centimeter, oh sorry, yeah, 1 centimeter, yeah, correct. 1 centimeter in radius. You can see it already. It's only the shape of the particle. So what do we need now? Just created it, shape, but no, nothing more. What do we need now? Thinking of probably something like the floor. Let's create the floor, okay? The floor should be a part. So most likely a plane, or if you want a box, if you want to have it in 3 dimensions, yes?
But you didn't put the like the qualities of the steel, like the.
Good point. Yes, if something like that comes up, please just interrupt. Good point.
And we have to create the second particle too, right?
Yes, and the second particle. Good. So yes, there are actually proposing. We have rock created that, right? But we don't have rock only. We have here. Even other people can just select it. Absolutely right. You can also just a short note. You can also use a mouse wheel when you move like that. You can just use a mouse wheel. That's very, let's say, intuitive. Changing stuff by the mouse wheel. Yes, we have something for rock here, but not for steel. Yes, steel should be set. And again, similar as before, you can use your mouse wheel with scrolling for changing the values. See what I do here? When I turn the mouse wheel, you can change very fast the settings just by scrolling on the mouse. If you don't have mouse wheel, don't worry. So let's say density. And in this case, we can also set a string or just a very high number. So we have a very rigid object. What is the density of steel? 750. Let's stick with the real one. Shear modulus, again, you were good to go with a simple, similar one as before. Let's stick with 20. We'll explain you in a minute why. And Poisson ratio the same. So probably the only difference is the density. Why? Because if you have interactions, and you recall that there was a very complex slide in my PDF where 2 particles come together with a lot of equations. And the equation said if there is a contact, we take a more or less Kirchhoffsche mean value between the 2 materials that come in contact to define our contact. Shear modulus was one of them. Another one was, for example, the Poisson ratio. So if 2 particles or radius, also the radius is 1 divided by equals 1 divided by plus 1 divided by. So if you have a contact and we have both with 20, so G modulus of 20, G modulus of 20, our mean value would also be 20. If we have 40 and 20, our mean value would be 30. Similar like that. Okay? So it's a mean value. If we set just the same, it's working quite fine. So we have our both materials defined. We have our particle. Let's define a second particle. Okay? So we have a mixture of 2 different sizes. Again, a sphere. Let's start with a sphere. You can try again later with some different shapes. Here we have a full drop-down list of different shapes. Let's stick with the sphere for now. It's easy. We're starting. You can try it on your own as well. You can also try it now if you want, if you're quite familiar. Define a box or something. Feel free. And we call that particle 2. You don't need to underline. Just I like it that way. No worries, yeah. Particle 2. And again, please no special symbols here. So don't write U, and sharp S. Doesn't work. It lets you put that, but it doesn't work. So let's define particle 2. Particle 1 has 0, 0, 1, and now we come with 0, 0, 1, 5. So it's a little bit bigger, and we already see the difference if we scroll through them. You can see the difference. And what would be nice, yes, if you have a density assigned to that, we can see the particle has a mass of, I don't know. Yeah, sounds good. Oh, what comes into mind here if I'm looking at that? Anyone with a sharp eye see something that's not in order? It's a very common mistake. A lot of people do that, and you will definitely do that as well. Very obvious mistake. What should our field should be made of? Out of rock.
Rock.
And
The
what is it made
material.
of currently?
The steel.
So, looks good. Define anything, just never mind the collision offset. This is a virtual radius that can put around like a half. Never mind that. And save. So we're good to go. So we have defined our first things. We have our, if we come back to materials, should be good by now. Actually, we should be able to simulate it, but nothing will happen because we don't have the source yet, we don't have the part yet, so nothing will happen yet. What we need is at least 2 parts, and I will explain you why 2 again. At first, we need a ground. Yes, where the particle should be set on, so something like a floor, but not a box. Just a simple plane is enough for us, okay? And you can see simple geometries are okay, boxed in that plane. If you have a more complex one, like a screw from a screw feeder, you need to import a magnet. So we will come back to that later. Just stick with the simple ones for now. Plane, we call that floor. And now we have a floor made out of a plane. If you have set the wrong type here, just delete it and create a new.
Wait, can you do it a little bit slowly?
A
little bit slower?
Little slow. Yeah, okay.
Please.
Again, just delete that again. So I switched to parts because now I want to create this plane in mid-air, right? In mid-air because we have nothing in our space yet. You can see that space is totally empty. We have defined in the background, if you create particles, they should be spherical with that size, but no particles there yet. Just an empty space. We create that plane. So we say plane, we call that plane floor, enter or add, and it's there. You can already see it, right? If you turn it, you can see that plane we just created. It's there with the default value.
Yep.
And the same thing as ever, if you just double click it, it jumps to the major information point box. Let's go through. The name of the thing is floor. It's highlighted in red. Seems good. It's made out of steel. And what is also important, nothing so far. Good. Where is the size? The next button next to it. So if you go to position, you can change where it is and a little bit about the geometry. So first thing, floor again, it's red now. You can change the position. Again, just by scrolling, you can change the values here, and you can switch it in mid-air. Probably a little bit, let's put it a little bit down, like, I don't know, 20 centimeters down, probably, okay? A little bit on the bottom.
What's the size of that square? You can choose the size too?
Yes, we come to that as well. It's 1 meter, I guess it's 1 meter. Because when you look here, or no, it's half a meter, sorry. If you see here down, the dimensions of this plane, here dimensions, length and width, you can change that again. Let's say half a meter times half a meter. And it seems the box is half a meter, half a meter, half a meter, obviously, because now our red plane here, highlighted in red, you can also turn it a little if you want. If you want, just feel free to do a little. I guess I love to turn a little in that direction. So,
Do this.
very simply, okay. Plane, right material, defined in mid space. Principally, we're not bad. Proceed. Safe. But now it comes. Where are the particles actually coming from? No one knows. For that, we also need a part. It is, and that's also very important to remember. In the M simulations, a source is always a surface where particles are coming out, like for example, a rectangular surface that is defined. That on this surface, particles are created in a certain pattern. So something like a material stream or a rain or the ceiling, where the particles should rain down in a certain in a certain way that we define later. So we need something like, let's say, call it generator plane or source plane. So we can call that generator plane so that you understand it a little better. Generator plane. And that generator plane is exactly the same as before, a plane in this space with 1 times 1 meter. We can double click that generator plane. Looks not that bad so far, but we want it a little bit smaller. I want it actually to be 20 times 20 centimeters, so very small, and on top, so it's higher, like something like
Plano
here.
generator.
Probably not that far, probably something like here, inside the domain. It should be inside the domain. Why, you think? Because what happens if my source is outside of the domain and the particle is generated? I told you at the very beginning.
They will not. They will be
Yes,
deleted.
they will be generated, but instantly deleted because they're out of the computational domain. Very good. Like that. Okay, so now we have a plane where particles are supposed to come out, and a plane where they're supposed to impact on. Good. Now we need to find how the particles are generated on that plane. And this is just below particles, because it's called particle generation. That's that part. And I would more or less follow that structure. Materials, parts, and or particles, and then particle generation. This is more or less the structure. Leave the other things out like collision, FEA, finite element, we don't need that for now. Let's go to particle generation, because we want to define how particles appear in our simulation. Because we don't want to have only one particle, we want to have a stream of particles, ongoing stream. Yes?
Oh, wait, can you repeat how you change the planes?
Yes, of course.
I get lost in there.
We will change that anyway after that, because you can play around a little, make, I don't know, a cannon, shoot anything with your particles. Yeah, just play around.
No,
But
este
for
está
now,
bien.
No,
planes,
porque es el
there's that we're defining here. I want to include
este
that
tiene que ser
plane.
el generator.
Not a box, not a cylinder, but a plane. Give it a name, for example, generator plane. And then it appears. And if I double click it, I want to bar here, where I can set the major particles, change the color, for example, to, I don't know, pink, basic things. And the second things are one part after that. You can change the size here, dimension, size of it, the orientation, and where it is in space. Should look something like that. Please be aware that the parts should be inside of the box, and we will come to changing the box in a minute.
degrees que grado le puso?
This is the domain.
Cinco.
Computational domain.
Cinco para tomar.
So far, maybe one actual good hint,
Acá está, este
because
es
when you
el-
look
el
from
arriba,
the
el
side,
generator.
you can't see those planes very good, right? There
Claro,
more or
de
less
abajo, de abajo.
hint. You can change the view here on display mode. You can change that you have an outline on your parts, which makes them also
This
visible
is
from the side. You can see that? If I change that to solid, I can barely see them, but if I change them to outline, they're better seen. This is only outline, I want to have it solid outline. There are different ways of viewing parts. For example, transparent. So I can see inside of the system. But let's come to that later. I'll change to solid outline. Also triangulated would be possible, but let's stick with solid outline. It's really cool for seeing the parts. Good. So far, so good. And now we want to define how the particles are raining down from that plane. So the particle generation.
Yeah.
Because this is what is meant with particles generated in the system. And then we see the type of generation. Yes, we have a generator, and the symbol says it. It's like a rain. You can also generate it in a different way. We'll come to that later. No worries. Okay, we generate instantly also a filling. But let's stick with the generator for now, because we want to have rain falling on our plane until it's more or less the heat point. Floor, should that be the real? Where do we want our particles to come from? What
The
do we
generator
generate?
plane.
Generator plane, right? And we give the generator a name. Let's call it generator 1 or 2 or 3. It doesn't matter. You can also name the plane and the generator the same. No worries, right? It's no. You can also name it XXX. Doesn't matter. It just needs a name so that it can again be defined by double clicking. You're already in the right box. particle generation generator 1. Yes, we want to generate particle 1 for now. For now, only particle 1, no mix at all yet. Just particle 1. From the generator plane, yes, that's right. How much? Unlimited, yes, because we want the stream to go on forever. And how much? 5,000 particles per second. Seems quite a lot. Let's stick with that. If the system can generate not that much as written here, for example, they go max, okay? They perform max generation. Let's stick with that. Yeah, and this is important also. They are generated in regular shape. Let's start with that one so you can see what that means and then change right after. Every 0.04 seconds sounds also not too bad. You can change it as well. We can play around a little so we can see the results. And we want to have also a good recommendation, probably also to write down an initial velocity, because when we create the particle, it has 0 velocity. So you create it and it starts falling down. Create it, starts falling down. So probably if you have something like an opening where particles are falling out, you should already have a little bit of a velocity, like minus 2 seconds, 2 meters per second, or if minus, why?
Because it goes down in the direction of negative.
Minus z means in that direction. Plus z, minus z. So the general convention is seen on the bottom left. Z is going up. So if you say my generation should be in minus z, it means 2 meters per second down. And this is a good, let's say, value, because I think anyone in physics, 2 meters per second is about half a meter drop rate or something. I think it's square root of 2gh. So 2 times gravity times h gives you, what is it? Time by Gauss, right? The time-free equation or something like that gives you a good indication. I don't have a calculator here, but probably you can type in the square root of 2 times 10, so 2 times g, more or less, times 1 meter gives you the velocity that you put. So 2 meters is not that bad. Oh, well, that's a common error in many of them, because last year almost everyone told me because no particles are coming out of their source, and it was just because of that thing that I highlighted here. So it says start generation at 0, stop generation at 0. So nothing happening at all. If you just put here, I don't know, a high number, 1,000 seconds, our simulation won't take that long, it just keeps on generating forever until you stop it. So, doesn't look so bad. Again, let's see if the simulation principally would work, because now we have more or less everything. We haven't set our focus on the domain yet, but we will come to that. For now, it should work. Let's go here. Oh, there should be something missing because there are physical time step here. But it should tell us anyway.
Simulation.
We have no simulation time step. This means.
Wait.
Sorry.
A little bit slowly.
For now, we are in the design phase, right? We are designing our system, not in the simulation yet. We just modeled our system, but we're not yet in the simulation stuff. So now we should actually switch from design to the next big block regarding simulation. And in the simulation block, we need to define some border points. And for now, interesting enough, we don't have a critical time step. Oh. Okay, and the safety level. Those are the two. Probably let's explain that again. We have a time step here. A time step, you remember that? This is the time we cut down our seconds for simulation. You remember? Particles moving in space from time step to time step. This is typically very small. Should be in the size range of, I don't know, something like 10 to the power of minus 5 or something. So something like that. Okay? And our safe interval, it's in the properties here, is the actual frame rate of our video we generate in the end. Like every, I don't know, 1,000 time steps that we compute should be a safe step. So compute, save. Compute, save. In between, there is nothing stored. Just compute it on the RAM and delete it again after that. So those are the two different times. So safe interval shouldn't be too small, because every safe interval 20 megabyte, 100 megabyte, whatever. And if you have lots of them, the storage is full again. So this is the computation. If you start the simulation, nothing can happen. Remember that it's on the computer, you can't do anything wrong. By just clicking start, if it's not working, it will just throw you an error. In actual, in this case, it doesn't throw an error, but there's nothing happening neither. So, now something is happening. You can see it. And pause. So you can see that there are particles falling out of our plane. And they're falling out in a rectangular and in a perfect regular pattern. So, now the question, who's with me here?
It fall apart. It closed the program.
Okay.
It's throwing too much, it burn out.
So this is the first try.
You see?
Yes. Okay. So let's get up to the end. Everybody can see on that. Yeah. Some of you have different multi-cores. That's depending on your hardware. My computer, I think I have 12 actual physical cores, and they're hyper-threaded, so I have 24. But I can use the 12 physical 10 miles with it. I think your license is restricted to 4 cores, if I'm right. And you can reduce it as it does. 8? 4. You have 8 cores. Okay. And yours is probably with the hardware. So you have 8 cores. I don't know the actual licensing. Well, they are limited to a certain amount. For example, on my website, I have 2 or something, but no worries, it doesn't scale. So doubling the cores doesn't mean you're double fast. It goes down probably factor 1.8 at first, 1.6 and so on. So it doesn't double your performance. So anyone not with me here with the particles coming out of the plane? Okay. Yeah, because yours crashed, right?
Yeah.
Let's start.
No, wait. I recorded in here.
Yes, they're coming out. Oh, generation rate quite high, yeah.
It seems the progress was not saved. I mean, I saved it constantly, but I reopened the file and all the progress has been lost.
Yeah, HFC.
Sí, peor. Espero que la esté.
No. I don't know.
Acá está.
No, I didn't say anything at all.
No, I closed it and opened it, reopened it. Because that same happened to me.
Pero eso hice ¿cómo?
Yo cerré todo y lo volví a abrir y me apareció todo el progreso.
No, que ya segunda vez que lo hago. ¿Lo abro desde acá?
Claro.
¿Este archivo?
Sí. A ver, ¿o guardaste?
No lo guardé.
Okay, so
Professor, which saving? ¿Qué saving time te puso?
Creo que será un-
Time step.
No. Tal vez se demorará un poco en cargar.
Simulation time, 1 segundo.
simulation start.
Let's see. Run. Start. Ah, no.
¿Qué vamos a hacer,
No funciona.
Pero un tanque.
Pero no somos ni los únicos.
It says you want what's missing.
A tu hardware.
And then to the party.
Tu harmo.
And yeah, you see, I know it's right here. After that, it gets state, the simulation.
Wonderful.
It doesn't matter. Just put the number here. I think it's 0.0015. We will address it. Okay? We will come to that because now we have that.
Yeah, we save it. The three have the same problem that we save it, but it doesn't show what we save. And I open this file.
The
I
program
think
crashed.
I don't know if double click is working.
No, I open it,
File open, yeah.
but it doesn't show anything.
Leave it open, leave it open. Okay. Not by double clicking. Open the software and then open in the top left. Try it
Okay.
on that way, probably. I don't know if it's just. I think it's just a trigger for the software, and then you have to click on the bottom, top left, on open to open the actual TPCAE file. Well, this is a TPDM file. Okay, yeah.
What's the file?
Yeah.
Is
Well, we
this
will
file?
come to that. Open. Open. No, this is new. That one, yeah. Open. And you have it. I think you need to go one folder up. Should be a TPCAE file somewhere. Where is
Now
that?
I save it in this.
Intro.
The only one that I have is this.
Let's try something because do you have the TPCAE file? Okay. Then go on File, Import.
These are the ones.
Yes, TPDM file, not TPCA. Go on File, Import, and time step. Try it that way, and then choose the enter, and then choose that file. Open.
Change the.
Open. Just open. Or import. Yeah. Because there is no working directory out there. Where do you set the working directory?
That's folder. Here in bold.
Yeah.
There
There is no TPCAE file. I don't get it. You should actually have a TPCAE file here. Yeah, here, right here. The same name as that one. I don't know why I don't get the TPCAE file. What's your path? What's the full path to the where are you working on? You didn't get the TPCAE file neither. Did you have a long file path, a long folder structure?
Yeah, that's why I wanted to ask you if we have too much folders that affect the processing.
Probably, yeah. It's better if it's a very narrow structure and sticking to the ASCII code. So it's easier to work, let's say, on E double point simulation rather than on desktop, a folder inside of desktop and go on, because then the structure is getting very long.
What do you comment for?
If you have the TPDAIM file, you can import that. Go on File,
TPG.
Import,
TP.
¿Cuántas carpetas ocupaste?
timestamp.
No.
And then you should
sí,
be
sí,
able
yo
to
te la tengo
import
en todo.
the TPDAIM file. Other one.
Está TPC.
Where do you save the
Cuesta el
Here he has the TPCA.
TPD.
Esa tengo yo, pero tú tenías el otro también.
Sí, este.
Show me the file on the system.
Where is this? I'm going to open it.
Yeah, the file. The
No,
actual
no puedo
file
buscar
in the Explorer.
Aquí. ¿Qué pasa?
We do some troubleshooting, right?
Claro.
Ausgegraut.
Lo programé para que funcione como clic derecho.
Dann lass die Simulation noch.
No,
Muss die
pues
Simulation
tenés que
stoppen.
sacar las pantallas.
Ein bisschen View auf.
No, I think I have to change the folder. Yes, the things that you should not, like a folder under a folder under a folder, because it's too much reading for the program. So you only have. Mine is like that. I know, but you have an information more than
Save as. Voy a cambiar Working Directory. Entonces tiene que ser una carpeta, solo una carpeta corta.
Claro, no.
Para que tenga una desktop. No funciona. This PC. Desktop. Era corto, ya estaba. University. Ok, si elijo esta así nomás, a ver, select folder. Ya, cambiar. Ok.
Lo voy a sacar de una.
Vamos a la simulación. Que lo guarde cada 0,1 segundo. Total interaction. Vamos a cambiar. Min interacción. Mencioné que fue hijo de eso.
I'm creating a new folder here. And all that up. Yeah, I think we have to start doing it again.
And I hate simulators. I hate simulators.
Hey, Monica, I already have the offer for the accommodation or something. You haven't applied yet? They charge me, the first deposit is 1 month, 500 euros, 250 or like, I don't know what the work they do for accommodation. I will end up for, no, it's as big a month, 500 now. Yeah. File? File? The first file? The third one. No, select one thing. Select folder. Select folder. Done. Yes. No,
Just if it's not crashing, if the particles are coming, that's good. Yes, we encountered there is one problem. There is some CPUs, very rare ones, not supporting just please alternate. Bitte wir reden aber mit der
I didn't hear you.
Working Directory. Pues lo cambié.
¿Lo cambié?
Sí. Select folder. Do you want? Yeah.
There are some rare CPUs where as soon as you can model it first, but as soon as you hit simulate, the system just disappears.
Yeah.
Sometimes. Very rare. I don't think that's sufficient.
Okay. It's everybody.
Really.
It happened for
Okay, then let's figure out.
Please.
change the working directory. Just follow me, okay? Click on File, Working Directory, and change it to a valid folder, which means no special symbols, not a too long structure. So if you click here, it should be not infinitely long. Scenario, something like C, simulation, rather short name. Not too deep. Generally, this should be something like a practice for every simulation. Keep the name a little bit short. No. Change that. After that, click on save. Call it shoot. Okay. That's the name of it. Then, very important now. In the system, in the install folder, are some examples. If you go to browser, see, you should do that as well. See, then to programs, backup, and where you installed that this is the install folder where you installed your repository. And there should be some folders like that. And there are some important ones that I wanted to address later. It is examples and tutorials. And those two are relevant when you're training and testing some things with the system. Okay? Then go to examples. Tutorials. And there are the three examples that you've seen at the start screen. The technique, the transfer chute, and the vBlender. And you can import those on your system and just hit the simulate button without modeling anything. And if it works, the simulation, your system is ready to go. If it crashes, your CPU may have some problems, or .NET framework is missing, and then I can provide you the .NET framework from the welcome. Let's figure out if
Can we try it? Can we try it?
Yes.
Please.
Transfer to, and then you have some files here. And the import are .env files. You can import them. .env is import. So let's go to sample simulation, copy that, and place it in the other folder that we just set it out at our
Sample simulation, INP.
So INP, yeah. It's human readable. I linked it with my Notepad++. It's human readable. That's in the file, and it's nothing else than a script executing all the steps that we did before. Set a material, set a plane, set particles. It's all in this 1.3 megabyte file. So everything, like you see here, add material, iron ore. Set material, density 3750, and so on. It's a very long script. Material is relatively long, and you can import them. So far, so good.
No.
So take the
No good at all.
transfer to INP file from your install folder and put it in your working directory.
No encuentro, no sé ni. Acá está.
¿Cómo se llama?
Ok. Backup 3D. Backup 3D tutorials. Transfer shoot.
So that's the transfer to. It is tutorials.
En carpeta C,
In that path. So
archivos de programa.
the install folder, tutorials, transfer to.
Archivos
That
de
should be
programa.
the path.
Sí,
So
por HTML.
backup 3D,
Backup
everybody. Anyone found that?
Tutorial.
Mein vBlender works.
Transfer shoot.
Ah, you're not in the
Transfer
browser.
shoot.
This is the opening.
Y ahí creo que es
Normal browser.
el.
Hay dos INP.
You need
Sample
Con Notepad. A ver. just one.
I have a second browser. Because I have
Acá
a
está.
second.
Creo que lo encontré.
¿Cuál es?
Okay,
Sample
okay.
simulation.
Esto de esto.
NP. Ya, entonces este lo copiamos.
Yeah, you're in the open file, just in a normal browser, just in a normal Explorer, in the normal file Explorer, not an opening. Just it here with that, with the normal. No, not with that file Explorer. Good. Yes, should look like that. Good. Yes, and that file, the .env file, .inp, in your working directory that we just
In the
defined.
working area.
So for the other guys, I will repeat that anyway afterwards. you can do file import keyword file because the .inp is an import file for pre-parting. Choose that keyword file, and then in your working directory, you just define set the IP file. You can open it. That should import you the whole system. So something that we did so far. We have three materials defined. C and raw particles. We have PTC raw, something like that. This is more complex than we have. Parts. We have several parts. Predefined in this one IP file. There is nothing more to do here. And save that one. Good. And click on start. And then the simulation should start working locally on your computer. If that works out, your computer is ready for the simulation.
Yeah, I did something.
Ahí lo corremos.
Import keyword file.
You know, follow.
And there it is. Double click it. Yeah, that one. And there it is. Now simulate. The simulation start. Yes, right here. Yes, save it first. Okay.
Simulation.
Choose your tests or whatever.
We should save it first.
Yeah, looks good. Save. Start simulation. And after that, the particles should start. Yeah, looks good. So if it happens that you do not see anything, probably you're looking anywhere in space and nothing appears. Okay?
Yeah.
Then just click on zoom in.
Ah, okay. There. Okay. Yeah. Ah, okay, okay. Okay.
That's the same thing, not only with the tube, but also with the segment and also with the V-blend. Just import and V-file and run it. One thing, because some of you already played around with the .enp file. .enp file means the actual simulation is taken and everything from the IMP file is imported without deleting the content that is in there. So if I import the segment into the tube now, I can show you what happens. What do you think it will happen? What do you think will happen? That's it.
If it doesn't delete it, it's going to show.
You play those? That's segment.
I can't simulate.
Rename that. That's the tube. So. Okay, I have the simulation and I say file import, and now I import another thing, and the tube is in there as well, the segment. So I can import and import and import, and it doesn't replace my initial one. So if you want to do that and then only the segment, you need to set a blank simulation first. So some of you already played around with that. If you want to change to the segment, just select new.
Me hace guardarlo antes de correrlo.
And then import the segment. Okay? Good.
30
Segment.
seconds.
How do you do that? Same as before. You have the
30
tutorial,
seconds.
the V-blender, the transfer to the segment. You click the segment, take the import file, copy it, so file, copy,
No, because it's so
place it here, for example, in a folder, or rename the other one, place it here, and then load that INP file again. Show you if you have that blank simulation. File, import keyword file. And if I take the new one, that one was it, that was the segment. Then there's the segment. And again, save.
You have to save the key.
Done. And it worked.
You have to
Very
import.
fast. So you get the systems very fast. That should work for almost everybody.
You have to import the material too. This other ENP file too.
No.
Only the first.
Those are two different ones. One is with, I think one is with multispheres and the other one is with rigid.
So you save it and then you can run it.
Save, run.
Okay.
Save, run, and should actually simulate start. Particles should start pouring out of the plane. Yeah, you either rename the other one. Yes,
You run it?
rename the other one.
And you erase everything. Then it's the program is the computer. Entonces tú le vas a poner shooter.
New.
Ajá.
File
Sí.
new. Yeah, file new, and then you have everything lined up. Import means load into this actual simulation.
Not exist. File. Working directory.
Yeah. Please do not. One thing. Please do not open the simulation system by double clicking a file. Just open the simulation from a desktop link and then open or file import. Yes, something like that. Not on double clicking on a file like on a Word document. Just open the application and then open the whatever you want. Everything good? So, who's so far with me in working with the SegMail or the Jute or one of those tutorials?
I simulate,
What did it do?
but
But you
again,
simulate
everything will go off.
Yeah, open Jute once more. No,
¿Cómo lo cambiáis de carpeta? ¿Cómo lo cambiáis de carpeta?
Directorio. Este lo tengo que guardar. Desktop, ¿cómo se llama esto? Transfer. Shoot.
Lo quiero correr esta hora.
Shoot simulation. Ok, entonces acá tengo las carpetas.
Simulation. No. No, hay computador, no se la puedo.
Ok, entonces acá tengo esto. Ok, este es el TP y este es el... Ok, so... ¿Y la simulación que le puso? 01.
No, no le cambié nada, corre.
Ok.
Tenéis que guardarlo.
Ah, ya.
Now we need to simulate this falls apart, right?
Yeah, me too. Professor Eric, do you have because for
Yours as
us-
well?
No. Yeah,
No, it
it's
crashed.
closed. It's exactly the same thing.
We'll install the .NET.
Thing.
Yeah, it crashed.
It crashed too.
I'm trying to open it again.
Please try not to open the file per se, but that one. Yeah.
Do you have some computers in the university
Yes.
that you can use for
Yeah,
work?
we have some. But I think actually that's about it. I will contact Alex and tell him which one we think so. So, on whose computer it's not working. So if you start simulation, the things crash. No, if you click on start, it just disappears. Who has this error? Yeah, you of course, you as well. I will contact Alex. Do you know something about your CPU?
Mariama, it runs for
Yeah.
you?
Either?
Really?
Mine is, no, in Ryzen.
Okay, AMD.
AMD.
My Intel, but it's an E5. It's not very powerful.
We had that, and it was the document.
Mi computadora vieja se la habría arrancado cuando dábamos por ese tipo. Tenía huevo mi computadora vieja.
58, yo pensé que había pasado más tiempo.
Y 2 horas.
Ah, verdad, pensé que había sido una hora.
No. Ah, loca, mi otra computadora tenía un huevo.
Esta wea refinada, weón.
Vos no te banca la simulación.
Tiene más weas que. ¿Y cómo se llama? No me acuerdo. Yo era un jugador de fútbol, así que no hubiera cachado.
Los nombres que conozco.
Sí, pero no hubiera cachado el chiste.
So, import. Y... Ahí ahora... Timestamp. No quiere importar un archivo. Open. Espérate. Ok.
Mira, chequear lo de María.
¿Ah? María.
Tiene el nuevo computador.
María Martínez.
No, este one. You have a big computer. Maybe that's the thing.
Ok. Para, ¿qué quiero? ¿Qué te para? ¿Qué te pasa? ¿Qué quiero? No, funciona. Quiero pelear. Pero afuera. Pero afuera. Igual. We call it work. Cool. Ah, for the teacher to see.
No, yo creo que es la memoria gráfica. Pero la tuya también. Ah, tiene. Ah, tiene memoria gráfica. No, se nos quedó el problema. Es ya, ¿no?
Sí. No, para, te voy a dar. Tengo ositos de goma.
Can we take a break, Professor, in the meantime? Because we're not doing it. Oh,
I'm not going to give up. Not on this.
Start. And then it's
not yet?
Yeah, save it, okay? One. Okay, save. Save, and then again. Start, and then it's gone, right? Wait a minute.
But it's weird because I thought it was the graphic card. For example, if you have a very powerful one, and it's not working.
Yeah. Do you have some antivirus blockers or something on there? That one is actually strange. Yeah, it should work. That's no, not the view. That's
For example, that about Yanno computers.
yeah, that should definitely work. Yeah.
Definitely.
Yeah. I mean, I get an update from the vendor for the plus redistributables that are needed, and if you install it, probably that would work. That would work. I think that's the main thing today that gets in most of the systems running. That's really important.
If I change the time step or something like that too, for now,
It's definitely
just to-
not in the system. Not in the software. It's something in the system. Either it's the wrong path, so you have no writing access. Typically, can be an error. If there is too less space available on that place where it's simulating, that could be an error. Graphics card could be one error, but to be fair, not a very common one. The CPU is a common error. Some of them are not supported, especially the older ones. Shouldn't be the case.
Yeah.
And he buy it this
Yeah.
year.
And last year.
What's
yeah.
the full path? C uses this. Yeah, and also the path is not very long. You have some rights
The
here.
working.
Yeah,
This is the working.
yeah, desktop. So that should work as well.
And the file, I selected
You
the
saved
des-
it, right?
Yeah, I saved it.
Yeah.
And this is I saved
Looks
it
good,
here.
yeah. And as soon as you click on start, it's gone, right?
Yeah.
Yeah, definitely. But yeah, that error, because your error is different. Yours through an error message, right? Yours through an error message, like send report. Yes, that's better actually. This one is worse. That one is better because then you at least the system detected something was wrong.
Yeah.
So seems that they are not the same. I will get an update for the C++. We will try install, and after that, probably if the error still remains, probably you can give me some hardware specs because the vendor says, okay, your systems are too old. But really, I don't think so. Actually, my laptop is from 2017.
Yes, mano. Vamos abajo. Parece que están dando comida, weón. Voy a tomar un break.
¿Tenemos pausa?
Sí, dijo que nos esperamos a break.
Qué bronca.
Focus on getting the system to run. Here, link like that one. That file. We see. I install that, please. And now again.
Unmute. Okay.
Here. Just take a quick get some details on
No, es que hasta
And
ya
then-
empecé a grabar acá.
resume the simulation. Yeah, it will crash at some point, but I can just readjust the simulation at any point. And if I want to change it from the beginning, you always need to go back to the very first, to the 0 time step, so to the first initial time step if you want to start from the beginning. But the good thing is you can also change it during the simulation. For example, if you want to stop something or a generation or anything, switch to the other, to the tube. Here, for example, in the tube, I already simulated. That's very powerful. Change, for example, the rate of filling here. A little bit more, a little bit less. I can do that at any point. This is the simulation. Now it's simulating, it's computing. You can see that here. It's slow. Then I click on pause. Go back in time, and you can forward to the last. Then I say, okay, 6 seconds. I actually wanted to change something. You can go back 6 seconds here. And for example, say I want to change the material stream here. More particles. Faster throwing them in. 4 meters per second. Let's see what's happening.
¿Qué le pasa?
Start. And I restart at 6 seconds with a higher material speed. I change, and you can see it while still here to outline view. You can see from the side that the material stream increased now. There's it's a little bit more particles than before. So you can change at any point. And that's important because lots of simulations do not allow that. So if you make anything, let's say a feeder on a screen, and you start feeding the material and say, okay, now it's enough, you can just click on pause, go to the generation rate here, and just set that to 0 or just delete it, and you now save it. And you click on simulate again, it just dots generated. You do not need to overall start again, just, and again, if you want to restart it again, let's say duplicable, and you want to add, let's say at 8.5 seconds restart it again, click on pause, design, particle generation, and again, activate it. Let's see what's happening. Again, the particles are coming here. So you can always pause, resume, and change things in between. If we now click on pause the simulation again and see back in time what happened, we can see that at first the particles were coming, then there are a little bit more particles, and suddenly no string, and again it's clear. So everything is saved. Where? Again, here, in this folder. Every second, everything that we can see here is saved here, up to 8.8. So 8.8 is actually that file here. It is 6 megabytes. All that is the simulation. If I switch to second 6, that file is loaded. So if you have very large files with a few hundred megabytes, it's a bit of a bottleneck because it needs to load the big files in your visualization. So that much to the structure per se. You can change anything anytime you want, and if you want to restart everything differently from the beginning, don't forget to get back to 0. Because you're always working in the step that you're actually looking at.
Okay.
So far. Now we have the simulation. That is one part. So we have modeling, means design of the system. Second part, simulation. Again with the tutorial for now. And the last part would be analysis. So we want to have something visualized in our system. That one. Here you can change the view so that that indicates something. For example, particles, the most common view would be particles coloring. I want to see the velocity of my particles. I want to see how fast they are. And now the color indicates the particle velocity. You need to go to analysis, particles, of course, coloring, and switch on for velocity. And don't forget to click on update. So you have, for example, between 0 and 8 seconds. So you have a good visualization of the color. If you only go for 8 to, let's say, 5, you can see that some are grayed out. So those are beyond that range. And of course, that works also during the simulation. So if you start the simulation from the beginning, you are coloring through the whole video. This is the first thing. So analysis of velocity, of energy, or whatever in here. If you want to have the string type, you have to change the behavior from solid back to dark. And you see some error in different sizes where the particles are flowing. So that indicates the particles. In your case, probably it's bigger. Who is bigger than me? You can change that here from solid to point view, to inside of the system, or to vector. That's good for analysis where the particles are actually going in the system.
Sacaste un montón. Ya lo sé. Hacelo la mona. Hacelo la mona.
Ya le digo.
What error? Working very good.
Oh no, come here. Mine is working. Okay.
What was it then?
questa modella ne sa forse mia perché
So you need a working directory where the files are actually stored. It's actually set. So it says working directory not set in the arrows. The first one was the working directory not set. Everything else was okay. Good, so it's working also in yours. So the VC++ did some good job. So who installed the VC file from Moodle? Just curious. Working? Not working yet? Not installed yet?
Installed, but it's not working.
Okay, please afterwards we will take a look here what's happening. But should be working?
Yeah.
Working?
Yeah.
not yet, I haven't checked it yet.
Who installed it already and it's not working? You're finished installing? Yes, but I think you have a different error. And the other ones all installed it and it's working so far. It's good, at least on this laptop. Okay. So simulation is working.
With a massive
Everyone who
graphic
is
card
now
for
working
solutions.
simulation without the program crash should be principally
Sì, non tengo
possible
idea.
in simulation.
Spero che mi ancora.
So now there was a short
Stata prima cosa.
simulation. This is a bigger thing. How something like that can be. Be principally now we figured out probably let's switch back that complex two only for now. Let's get things back probably to a blank system and open again our first test simulation. If you still have that, otherwise please just make a new one. So we have our base simulation with two planes.
Sì, l'hai passato.
The basics are the same. So we have the public and I wanted to stop here on because we back to our simulation. So forget the tool and segment stuff. That should be more or less right. Yeah, are they coming up? Yes, good. Okay, so we have that the particles coming up, and they should actually fully fall. They should go through here. Why? What's happening? We define the particles, we define the plane, we define that they are falling out there, but why are they? No collision is defined yet. Right. We said we need a Hertz-Mendel contact model, something similar, so that the particles know that they actually contact each other. So we go to interactions. Oh, yes, there is something missing. Rock has no interaction, and rock steel has also no interaction. Nothing defined here. One minor thing here. I just said that. I changed something and I changed it in the current time step. Not a good idea, right? Because I'm at 0.4 seconds. I actually need to go back to the very beginning and define it here. So from the very start, at second zero, here also, second zero, I need to define that there should be a contact between rock and steel. I change material A rock, material B steel, or vice versa, doesn't matter. And I said, which contact model, please don't look into that, just select the default one. There are lots of them, as you can see, predefined, and you can change any of them in detail, but just let's add the default contact model, dry Hertz-Mendel no-slip contact. So we say, contact between rock and steel, defined. No slave model, no stickiness, no cohesive behavior, just dry material rock to steel. We double click it, And we have some details to fill in. We have A, B, C. A lot of stuff to go into, but as you remember, what this might be, restitution. You remember? Particle falling from a certain height, jumping back. Let's give that 0.2, for example. So I want to have that something like that. A little bit damping, not too much, not too less. Let's start. Something between 0 and 1. 0 would mean, and 1 would mean, okay? So it's the restitution that jumps back of the particle. And we have some friction parameters, also between 0 and 1. And that should actually be calibrated. But we start with some values that I know. 0.3 works quite well, and rolling friction a little bit less. So static should always be a little more than dynamic. It also says that to you if you started and you did not do so. So let's start with some values. And again, save. And now, if we go to simulation again, and we start, particles should fall out of the ceiling at some point at least. Yes, they're here. And check, I mean, it's very slow at my computer because I have a very small time step, only 2%. We'll come back to that. So, does it work? Point. Yes, we have contact, a little bit of jump back, not that much. And the next particles are coming. Let's see from the side what's happening.
They won't collide.
Yes, they won't collide. Why?
Because we didn't define interactions between
Same
particles.
thing as before. Absolutely right. So we can go back, interactions, and we define rock. At rock. Similar as before, but I want to have stone to stone, even with a little bit more damping, like 0.1 or even below, something like really, let's say, like rocks. Rocks do not do like that, like steel balls. Rock are more, let's say, damping. 0.1 and static friction, I choose just the same, so I have starting values. Again, save, and I start the simulation. And before I start now, it's really slow, not really what I want. You can see here 2.64%. Doesn't say that much to you, but probably you remember also from the lecture, there was a time step that was critical, the Rayleigh time step. And it was like this shock wave going through a solid particle. If you have a very rigid particle, a very small particle, you need a small time step. The program automatically computes in the background a time step that is suitable. And 20% of the time step is a good value to start with. So I changed my time step that here is about 20%. 26, 30 might be okay, but it's probably not stable anymore. We'll show you in a minute what that means. 26 should work. I want to simulate not 1 second, but 5 seconds in total. Again, I save, and I start. And it should be much faster. Yes, particles are coming out. And we have contacts. Perfect, looks good. So we are already at second 1. Particles that leave the system are deleted, you can see that here. And the particles are more or less thrown here on the plate. Now, with the pause, I can also change the time step at any time I want. I already said that, right? I can change anything at any second. Stop now. And now I will show you what it means if the time step is critical, right? This would be a supercritical simulation. Time step is much too big. If anything like that occurs on your system, go back. See, at first it's stable, some point. That is a stable time step. So as long as the simulation stays like that, it's okay. As soon as the particles explode, poof, everything goes apart. Simulation is super stable. Good. Now another thing that I did not want it. I said I do not want this perfectly regular patterns to occur. Probably go to design, particle generation, that's where we left before. And here is regular. Let's change that to Poisson, which means randomly distributed, and I want a little bit denser generation, so more particles after another, so not every 0.2 seconds, probably every 0.05 seconds, or whatever. Save, so the insert interval is denser, so particles are not entering like pop, 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 raindrops much faster. Safe, and let's see what's the difference. Yeah. A denser particle stream, more particles, and we're shooting our plane here. Cool. Everyone so far with me? Not. Okay, but we will repeat it anyway once more, but with the box. Yeah, you already get it. Good. We will do it again with the cylinder now. We'll do it again, and everything that you did not get up, you can follow up, okay? So, now we have tried the first thing, the first idea, the first concept of a plane in mid-space, pouring a heap on it. Now we want to fill something. We want to fill, and that's the first thing for our lab report. Probably you can also consider that as your example for the report. You feel free for whatever you want. Now you get an idea what is the effort, and it's a lot, of course. But if you're into it, it's quite, let's say, straightforward. Now let's start with our second idea. First one, plane filling with particles. Now we want to have a cylinder on a plane. We want to fill the cylinder with particles and then lift the cylinder so we get a heap. What's that test called? Lifting cylinder. Exactly. Perfect. You're ready for the exam. No. Let's start again from the beginning. New simulation. So everyone that didn't catch up here and there can follow now from the beginning, right? Very grüne Wiese. Green lawn. Yes. Yeah. If anything is missing now, contact loss or particle generation different or anything like that, we will address that again here. We will do the whole thing, but not pouring on the plate, but pouring into a cylinder, filling the cylinder, and then lifting it. So now not on a plane, but into a cylinder. Like contact, do it again. Now, so new setup, blank. The first thing that I said we should define the material. Right, very material. First material we call it bulk. Bulk material, and the second one we call it steel or rubber, or let's call it steel, and the second one we call it black steel, like our cylinder of the lifting cylinder. Good, so we have three materials, bulk, steel, and black steel. Again, double click, bulk, again 2500, good value to start with. J modulus, let's stick with 10, also good value, very fast. The lower the faster, by the way. I can show you in a minute. And we just put the steel again, 7850, doesn't make a difference because it's rigid anyway. J modulus, again, 10, Poisson ratio 3. And last material, black steel, I don't know, 5,000 probably. It's rigid anyway. Shear modulus, again, 10, and Poisson ratio 3. So we have more or less three very similar materials. Safe. First thing, safe in our system as before, we call the lifting cylinder test. Safe. Good. Second thing, now we define materials. What now? Yeah. What should we proceed with? Parts or particles? So what should we do?
Particles.
Particles.
Let's go to the particles. Okay. Again, maybe something different now. Probably
Could be
what should we choose?
multi-sphere.
Could be multisphere, but then we need to define several spheres. Probably stick with
Torus.
Torus, you like Torus? Okay. Call them Torus.
Torus? Okay.
Oh, I call them Tours. Doesn't matter. Tours. Okay. Tours. I need to define alpha diameter.
Good looks.
Centimeter, and the radius of the set. Oh, actually, yeah. You like that? Looks good. Safe. Now we have our donut. Then we define our parts because we want to build something, right? And therefore we need at first a plane. Pre-selected. Okay, let's say plane. We call it round. double click it. Looks not too bad. Let's stick with that. Then we need a cylinder, obviously. We call that a cylinder. We double click it. And go to position. Here we can define the size of the cylinder. Are you with me so far?
Yeah.
Go. Define the change anything. Double click here. Change the where do I magnify? I don't know. Does that make sense? Should I turn up the size a little? Or is it okay? Perfect. Does it work? Okay. So I defined that parameters for the totals. So 0.05 for the outer diameter, 0.02 for inner diameter. And I forgot something very important. What?
Find the material.
The collision of.
Find the material for the particle.
Yes. It should be made out of bulk instead of flexing. Good. That's a very common mistake, to be fair. After that, I directly switch to parts. I define the ground as a plane. Plane, we put here ground. And then I define a cylinder and call that one cylinder. Very quick. But the cylinder is not defined yet in its size. So we have the ground with 1 meter times 1 meter, that is default. But you can't see the cylinder because when you go to position, a cylinder has no radius and no height yet. So if I increase that a little, I can already see it a little. It's too big. Let's say, I don't know, 25 centimeters would be good, I guess. But I think it's the size of the thing we have in the lab, 25 centimeters in diameter, and half a meter in height.
No, you put 125.
Yeah, that's the radius. So it's 250 times.
Okay.
Yeah. Yeah. Okay. One problem now. The cylinder is not on the ground. We need to lift it a little. Exactly quarter of a meter, so that it's on the ground. Looks good so far.
Yeah.
And we need to remove the bottom. So now there is a bottom and a top. We can remove the top. And we remove the bottom, so that it's a hollow cylinder. Good, right? So far so good?
Yeah.
Good. Save. Okay. Victoria? That's a plane. You need to go to parts. Delete the cylinder because it's a plane. Delete. And select cylinder, yes, select it. And now call it cylinder or suit or whatever. And now double click it and go to position. Now it should be there. Yeah. No worries. If anything occurs, just interrupt me so we can catch up. Or if you say stop here or go back, please do that because I don't know the speed if you don't interrupt me.
Okay.
But you have the cylinder now on the plane, sitting like that. If we want to pour particles in, what do we need?
A particle generator.
Plane generator. Right here.
Generator.
Plane. We call it again gen, plane, or whatever. Generator, something. But it needs to be a plane. Yeah. Plane. We have the chain plane. Yeah. Good. Go to position of this generator plane. It's already red. And we lift it up. That's the first thing. It above the actual cylinder, probably not that much above, and lift it, something like 5 centimeters off the cylinder. So 0.05. Much too big, most of the particles would go on the sides, so we'll make that a little smaller. What work? like that. Should work, hopefully. Good. So we have that. Last thing that we need to check, if we go here to our ground, what do we see here? It's made out of plexi. Should be steel.
So Eric, can you change the generator with another shape?
Yes, with a workaround, but let's stick with a rectangle.
Okay, okay.
That you can change that. I will also show you something different in a minute, but let's start with filling it up with a plane and then try to fill it at once. Not with a rain, but with a instant one-time filling.
No,
that as well.
yeah, because I thought of some real operations.
You can do that.
Okay.
You can choose a different. We can do that if you want. We can change the plane and instead use a cylinder for a generator plane.
Okay.
And if we put the, I will just do that because it was so that position a little bit higher, like here. Yeah. And you can use that as well to say, okay, the height and then fit, yeah, something like that. But you need to define that this cylinder is not collision detected.
Okay.
So you need to turn that off, and then it can be used as a generator plane as well. You can also say that it's not shown, but we can try it with that if you want. I hope this works for donuts. I'm not quite sure yet. Should actually, but yeah, let's try it. Let's try it. There's something new. I will just set it to the same diameter so that it more or less fits the opening here, and then the donuts should come out here on the bottom. If the donuts are not too big, I hope. I don't know which size we made, but we will see it in a minute. There can't happen that much because if something's not working, just try to change it. Nothing's gone. I will try it with that. You can try it with the classical planes as well. No difference, okay? No difference. Just stick with the planes so far. I would recommend it. Yeah. Probably I will even change the opacity a little. Let's say 50% so I can see inside of the yeah, something like that. Good. So I can see inside of the system. Here you can change the transparency of the system. So you found that probably out on yourself. You can say outline view and transparency. Okay, we have the generator, we have the parts. I wanted to check the parts for material. The ground is made out of plexi, that's not right. Ground should be made out of steel. The cylinder should be made out of plexi, and the copper thing out of plexi but polished off. That's my current setup. So now, we need to define the particle generation. And here, that's what I wanted to address before. You can use generator, classical one, coming out from the generator cylinder here. That's the classical method, but you can also use a filling. So you can fill a whole volume with particles at once. Not layer by layer, but the whole volume. But let's start with the generator and say I want to make a gen from, and that's important, from the generator plane above or the generator cylinder above. If I double click it, I see it again. Now that should be red. The thing above your cylinder should be red. You still go with me? Mm-hmm. Either your plane or my cylinder should be red.
Yeah.
Yeah, torus should be coming out there. Wasn't so bad before. Let's start with velocity. 2 meters is okay. Downwards. Start time and stop time, very important. Most of the people forget that. And that should be it. One major thing, our domain. The domain, if you look at that, not working with that because our particles are generated here and would be deleted instantly. In the last simulation we didn't address it because we stick inside of our domain. Now we need to adjust that a little. So here you can change the size of your domain. And a good start point would be automatically update and try to fit everything around the particle, the boxes, except that one that is set to no collision. So you need to adjust that a little in state, a little bit higher, something like that, and you're good. Just doesn't look so bad, right? Everything is inside, looks good so far. What is the cell size? So here, you can see that this is the cell size. And I also do not want to exaggerate that, because this is a science for itself. appropriate setting of the cell size. A good rule over the thumb is to set the cell size above this in the area of the size of your smaller particles, So if you have a very small cell size, for example, like that, much more cells. More to compute. If it's bigger, something like that, it's okay. Not that much cells, in about 1,000. That's okay. But the computation of the contacts might be a little bit more complex. So there is a trade-off in either direction. I would stick with a value around the size of your particles, and I remember we have an outer diameter of 0.02, right? Something like that, or 5. So it's not that bad in that area. Probably a little bit smaller, something like that. A little bit more, because 1,000 is nothing. 1,500 still not that much. Let's see. But turn the grid off again. This one is important. So that all of our parts are inside of the domain. Otherwise, it won't work most likely. Save again. Call the simulation. And let's see if it's ready for run. Okay, now it's showing me the this should be set default. Yes. Let's see. Okay, there is something that's not an error, doesn't throw me an error, but no particles are coming in my system. Are in your system particles coming in the simulation?
Yeah.
From your plane? I will try changing it to a plane, okay?
Yeah.
I don't know if torus
llenando con
particles
donuts.
work with that form of inlet. It's possible.
Porque dijiste plano.
Mira.
Uy, la media zona.
Pero están atravesando, claro. No puse la colisión.
Because I do not often work with generated plane made out of cylinder. See, that is the issue. No. I will change to the plane. Who has a plane? Is working with a plane?
Yeah.
Then that's probably an issue. Is the size okay? I will just do it.
No, I think the torus should be
The
smaller.
donuts are, yeah.
Should be smaller?
Yeah.
They're quite big, right?
Yeah.
Yeah, I thought so. I just
Should be like
tried
Fruit Loops.
myself.
Oops.
Let's see. That would be too big.
Oh, ella es más chiquita.
Let's see. Not regular, but Poisson would definitely be a good idea. And let's see. Yeah, they're quite big and no collisions defined yet, but they're too big, definitely. Yeah. Make them a little bit smaller. Actually, it should be possible to change them during the simulation so we can see how big they are. Go to design, particles. 2 and maybe that doesn't look too bad. 2 and 1.5. Let's see. Yeah, that looks better. So it was, what was the size? Don't forget to go to 0. What was the size now? 2 and 1.5, right? Okay, I changed that to that. I leave that open. Should work with that. And at second 0, because otherwise it won't work. Okay. Everyone so far? Not working. Not working?
Yeah. But they are so big.
The program?
Funciona. Falta el tamaño de los torus.
Okay.
Yeah. Déjalo dice. Ah, me faltó guardarlo.
You
claro.
have no mouse, right?
Hmm? Yeah, I have to set the video. I have to finish the video.
We will change the generation. We wait. No?
Mate, mate.
Ah, yeah, we changed that as well with the cylinder. Yeah, we will remove that. Okay. So now, yeah, most of you see there are probably now try a different method. At once. By which is not a bad idea, but we will try to do it definitively. So we try to right instead of using that plane here, did the generator plane? Did? Yes. Then it should look something like that. So we have a plane, an empty cylinder, hollow cylinder, and now we go to particle generation. Instead of selecting generator coming out of the plane, we select filling. So we want to fill something, and in the end, we call that fill. We want whatever fill. Double click on fill, and there are some things to set. What do we want to fill? We want to fill colors into a box. Primitives, yes. We want to fill a sphere with a radius of, a cylinder with a radius of a certain size and a height of a certain size. Now there is something defined here, a volume, you can see that already, and that volume will be filled with particles. You can already try that if you click on add. And you see that volume is more or less filled with donuts. We don't want to fill it regularly, we want to fill that in a Poisson manner. So randomly distribute the donuts inside of this brief. Delete them if you please don't click on add several lines because the donuts will overlap. They will add it. So just please click once, add, and you see that there are some donuts. So far?
Yeah, yeah.
Filling. Select the cylinder, Poisson, and the direction of the donut should be in the Z direction, so it's upright. And you can change the position of it. Definitely, you want to go up, like that, and slightly donuts in this filling. But yeah, that's not enough. Say, what we will do is we want to increase that volume that we want to fill, but triple the amount of the cylinder, so like that, like that, like that, so, and fill that volume up with donuts. It's working now, but as soon as I click on simulate, all the donuts up there will be deleted. So I need to also change my domain, so that the donuts are inside the domain. So I have a tower of donuts ready to fall into my cylinder. I have full control how many donuts there are. It's a little bit more convenient in lots of cases when filling something. Instead of pouring something in, you can just define a volume, for example a sphere, or a box, or a cylinder, and fill them. You can also, what's also interesting, you can move them. So if you want to have several of them, probably here a few, there a few, you can change that anywhere you want. I mean, it doesn't make sense here, but if you want to fill 3 side-by-side cylinders, you can just fill, and let them stand in. Okay. So I have my donuts here, and when I go to simulation now, they should, what should they do? Let's see if anything happens. Nothing happens. Why? Very, very, very important thing that we have here on Earth, different to the moon. Gravity. We didn't define any gravity yet. Design. That's also a very common mistake a lot of people don't think of. Loads, there is no gravity step. On loads, there is a bar that means gravity, and you need to have gravity in the z direction, minus z, minus 9.8 or whatever.
Yeah.
Safe. And now, let's try it again. Again, at time step 0. Start. Yes, they're accelerating down. No contacts yet, of course, we didn't define any, and the particles that are outside of the domain are removed. Toss, back again. So far, gravity, feelings, good. Who's with me? Good. At least one. Now it's actually learning by doing, and if you do, I will show you also. I mean, it's 12 now, but I will show you in the end some of the tutorials where you can click through. There is also a PDF with transcriptions, easy to follow, but most of the stuff is learning by doing, and that's also why I'm not a big fan of recordings, because anyway we have the PDF, so I don't need to record a lot of stuff because the PDFs are there. But so I can more or less go up there and do a little bit, see where you're missing some point. Good. Donuts? Who has the donuts already on his screen visible? Good, good, good. That's good, yeah. Filling?
But I activated gravity.
Is that the filling?
Yeah.
Holy macaroni. You're trying out a little on your own. Yeah, no worries. If you want to try out here and there, add some contact mode already, no worries.
I activated the gravity, but I don't.
Gravity is very important because otherwise down. Last thing, same as before, same thing. Particles and particle generation, and in the end, interactions is also important. And don't forget the domain if you have troubles with your size of the system. The domain should be around this. I will highlight that also in the end. So let's go to interactions. Yeah, we need interaction between bulk and steel, and between bulk and bulk, of course. We need between bulk and flexi. That's it, right? That's it. Everything else is cool so far. Bulk and steel is the first contact to the floor. Restitution of 0. Donuts are quite soft, right? 0.1. Static friction higher, I would say 0.5, 0.4. Bulk, I would say, ooh, this is even more soft, 0.01. Just put some values here so that I can proceed. And flexi is a little bit, I would say, here again with steel. And 2. Okay, I put some values here so that I can proceed. Okay, I have 40% of my radial time steps here now. I can increase that a little. Okay, not so bad, about 30%. It's quite high, but hopefully it will be stable. Before I click on simulation, I want to show you what the shear modulus is all about. Why we set that with 5 instead of 10. Now remember, we have here 30%, around 30% of our critical time.
No sé si está
If I
funcionando.
change my shear modulus,
No sé si está funcionando. Que no se mueve.
¿Será?
Ahora sí se mueve.
66%. So decreasing the shear modulus gives me
Ahora
a
funciona.
much
Ahí se
more
salieron los
simulation.
Tengo que
Decrease the
donuts.
shear modulus.
Entonces, ahí me-
Change that here. And only for one of them, not for the
Piso.
three of them.
¿Le pusiste piso a eso?
no le puse interacción.
And hopefully safe. Let's see. And the donuts are in my box. And at some point, somehow they have to be. Let's see if I can find any.
Funciona.
Right. Rice brown should be made of steel. Next here. Okay. Particles are made out of pulp. This should work as well. So probably this is too much. Let's see if it's. Let's see now. Probably 30 was too much. What's happening? Let's see. Yeah, looks better. So 30% was critical. Everything went unstable and the donuts fell out of the system. So looks good. Fit, not so bad, right? Oh, unstable again. Yeah, you see that? At some point it suddenly gets unstable. And that's probably also one thing with spheres. The critical time step is working quite well. As soon as you leave spheres towards donuts, bottles, like objects, boxes, cylinders, capsules, something like that, critical time step gets a big problem. So this is too high. We'll go down even more. And this is actually have you received the project studies yet? No. Oh God. You received them? The Austrians know what I'm talking about. So there are some project studies here that you need to do, and I propose one. A very, let's say, simple one where you do not need the lab too much, but the computer. So I would propose anyone taking that project study should have a computer with the software running that I just gave you. So you should have the running system, and the idea is just to change different particle sizes. So change to donuts. So start with spheres. Find out the critical time step. So okay, let's drop a sphere on the bottom and stable. Everything good. Increase the time step a little. Unstable, catastrophic. So make a Newton's approximation and find the stable time step. So I decreased it, and 0.05 works like charm. So particles are in there, they're moving a little, but that's it. If I increase the time step to a certain point, let's see what's happening. I increase it to 0.01 and I start, and the thing suddenly starts at some point. Okay, that seems kind of critical on the limit. Let's increase it even more. And boom, unstable. Going back. And again, so I find out which time step leads to an explosion of the system, right? And I want to do that for different particles, so for cones, for capsules, for stones, for different shapes of particles, and find for the same size of the particle in volume, for example, in volume, which time step is critical at which. So I have a table, which time step is critical for which shape. That is a very, let's say, the Z direction with 1 meter per second for 1 second, which means 1 meter instantaneously, so no ramp or something, but just starting to lift. And let's see if that works out. Start. Yes. And our cylinder is lifted, slowly but steady. And you should see at some point that hopefully, depends on the friction, that some particles are falling out. I mean, this is slow motion, right? Don't forget that. They're a little bit interlocking. Doesn't look so bad. Don't forget this is slow motion. We are just at 0.7 seconds. And the second thing you can already see is that particles are also sticking on the wall. The friction on the wall is quite high. So probably changing the friction on the wall a little bit to lower values would help. Yeah. And probably the velocity is also quite high. 1 meter per second is like that. So yeah, I think at the lab we are running with 6 centimeters or so per second. So yeah, and that's it. And after that, 1 second, simulation is over. If I can see now, okay, I want to have it a little bit longer. I can even extend that. Say it should run further than 1 second. And in the end, I got something like a heat.
Le metto in movimiento para levantar el cilindro.
Yes, that's a good point.
Uso movement.
En diseño.
So, the question was, if I change something at 0.5 seconds, times that 0.5, for example, lifting of the cylinder, and I go back to second 0, the lifting is not there, right? Yes, and that's the case. So I typically, when I know I want to lift the cylinder later on, I define from the beginning, so here, here, no, right? Not defined. Some point, 0.5 exactly, there is the cylinder lifting, suddenly appearing. You see that? But it's not there yet. What I do is I define everything at the beginning. Define a lifting here. Say the lifting should start at 0.5 and end at 1.5. That's the idea. So I define more or less everything at the beginning. If you want to figure out if something works, also in your case, if you want to change something later on, you more or less, most likely, will work on one setup. And you can change here and there and there. So it's a work in progress. 330. If you want to do it, let's say, academically correct, a master's thesis, for example, it's architect, for example.
¿Qué más tenemos? ¿Una fiesta de la noche?
No sé si me da.
He's looking at the bucket made out of material A versus the bucket material B. Material A, exactly the same material in both systems, and he turns it over. So the bucket is level, right? The unloaded material. And she's analyzing which material A or B performs the least better. More or less. That's the idea. She's doing it with that. So she defines more or less everything at the beginning. The movement of the bucket, the forming of the material at the beginning. So I will define as much as you can.
No lo vi.
In our case, we
¿Para qué?
start the lifting, right? Was it at 0.5? 1 second? I don't know. So I set the ticket, let's start the lift. And tick on
Está grabando todavía.
at 0.5. Around was a good
Pausa
time
lo.
because but